We're going to talk about dynamic mechanical testing today. So previously we were working with Kelvin-Voigt models, Maxwell models, standard linear, solid models, Boltzmann superposition principle, creep compliances, relaxation moduli, and we were seeing how these models were getting really complicated. So we don't want to necessarily have to, build and develop these theoretical models for every single polymer that we deal with. So instead, we could use a more utilized technique, characterization technique, an experimental one, which is dynamical mechanical testing, to look and determine some really critical parameters like the relaxation time of your polymer, and to see where our polymers, under what conditions, time, temperature, and essentially frequencies, when it's going to behave like a viscous fluid, when it's going to behave like an elastic solid. So you could kind of imagine that we have this kind of cylinder, and I put my polymer in this cylinder, and I have another probe here, or not a probe, but basically a kind of another cylinder here, and I am going to kind of push this down, and I'm going to apply this kind of cyclical kind of stress, this kind of sinusoidal stress. So that's actually described right here. So I'm going to twist and move this kind of like little plunger into my material here, and I'm going to twist it. I'm going to twist it at different frequencies. I'm going to vary those the frequencies at which I kind of rotate that little kind of mini plunger there. So I'm going to apply a sinusoidal stress. So we're going to apply this stress, but we're dealing with viscoelastic material, so there's going to be some phase lag in the strain behavior. But the strain behavior will also be sinusoidal as well. So this is our applied stress. Our strain should behave like this, but we are going to have, again, some, basically the material will also experience essentially, this is essentially the strain, again, the applied stress that we're applying, the strain will also be sinusoidal, but there's going to be a phase lag. So the material is actually going to develop or actually experience a stress that contains that phase lag delta here. So if you just do some kind of, again, some trig function expansion, this is going to be our terms for stress. And you'll notice here we have the first term. This is going to be in phase with our, basically with the strain, or essentially this is going to be our elastic response. So this sine of theta, is going to be out of phase. So our second term. So this is going to be here. This is going to be out of phase. Because again, you could kind of see sine, so it's in phase, cosine is going to be out of phase. So this is going to refer to our elastic response. This will be our out of phase component, which is going to be our viscous response. So we'll come back to that in just a second. So with that definition, we could actually describe two different elastic moduli to kind of basically encapsulate this in phase and out of phase kind of component to our stress. So the storage or the elastic modulus, i.e. the in phase contribution, can be defined just like this. Again, using kind of the Hooke's law expression. So for our strain here, so this is going to just be this E prime. The loss modulus, which is going to correspond to our out of phase component, that is going to be, again, this is kind of the idea here. So you have some, applied stress. There's going to be some in phase component. So here, and there's going to be some out of phase component. So the in phase is hooking and elastic. Again, this is our applied, basically we apply a stress, there's some resultant strain, and we're going to have some component here that's out of phase by this delta right here. So there's going to be an in phase component, an out of phase component, and that's what's described here. Our loss modulus, which again it corresponds to the viscous component or the out of phase component, is described as such right here. So you could rewrite that expression with those definitions now as so. So it's just going to be this expression right here. So you're just plugging and chugging kind of into those definitions. We could kind of look back and see where those essentially can come from, and using this idea that, remember, this is our kind of applied strain right here. So we could rewrite those expressions, and now you could also define this really critical parameter called the loss tangent. So this is the amount of energy lost over the energy stored. And you could also rewrite this expression. We'll come back to this kind of a loss tangent in a second. You could also rewrite this using complex variables if you'd like. So you'll see this a lot in kind of literature as well. But again, it corresponds to the same thing, but you kind of see the in-phase component versus the, sometimes you'll hear this as the, not only the, basically the storage modulus here, or the loss modulus, you might hear it as like the real or imaginary kind of moduli. So you'll kind of see this, you can see the in-phase component is our real component, the out-of-phase or the viscous response is our kind of imaginary component as well. But it's the same kind of idea, same concept here. So this is kind of just a definition and how this experiment is run, and we're going to get into kind of a really cool analysis in the next video. So I'll see you then. Thanks.